exciting definitions of energy. So, what's true? What's false? Who knows? That's silly. I'm the teacher. I know. So, 11a. Which one of the following is a true statement about energy? Well, it's not destroyed due to frictional forces. It just gets transformed into a form that we can't access. Energy is a measure of the ability to do work. Yes, this is true. More energy is available when there is larger power. Well, more energy is available per unit time. But maybe we have a really powerful machine that's turned on for just a tiny fraction of a second, and then a really lame, weak machine that's turned on for hours, and over a long time, that really lame machine generates more energy. So C doesn't work. And energy and power are not the same quantity. Power has units of joules per second, and energy has units of joules. So don't confuse those two. So it is, in fact, choice B. And then for number 12. Boy, you notice how we seem to keep comparing kinetic energies of things, like all the time, forever? So we need to compare kinetic energies. So EK of the first object is going to be 1/2 mv squared. Oh my gosh, why is my friend texting me while I'm trying to record videos? This is insane. I'm going to turn off notifications. It's so embarrassing. Okay, so EK is 1/2 mv squared. And then the second, we're just going to ignore that happened. So then the second thing, even though it's on a YouTube video, you can replay this over and over and over again to your heart's content. All right, so this is the first mass. 1/2 mv squared is its kinetic energy. And then for the second mass, we have EK equals 1/2 m over 2 times 2v squared. So this ends up giving us 1/4 m times 4v squared, which gives us mv squared for the second kinetic energy versus the first. So what this means is that EK2 over EK in the first situation is going to be mv squared over 1/2 mv squared. And when we actually get this fraction worked out, we're getting a ratio of 2, or choice C. And then number 13, we got forces, we got speeds, we got distances, and we want to get the work done on this box. So, and notice we, and here's the thing, it's moved at constant speed. So what does this mean? Work is the change in kinetic energy, and the change in kinetic energy is 0. Let's be clear here, though. Friction does work equal to negative F dot S because it tries to slow it down. And then the pushing force does work equal to positive F times S. And so the total work equals negative F times S plus F times S, which is a big fat 0. The work done on the box is 0. The work done by friction is negative F dot S. The work done by pushing is F times S. So the total work put into the box is a big fat 0 because you're losing energy just as fast as you dump it into the object. And then question 14. This is an efficiency problem. So to get efficiency, the power produced is 200 watts. The total power we input is 250 watts. And that's going to give us 0.8, which is 80%. And then the last question, number 15. Como problem. What is this? Como problem. What? Ugh. Just get rid of that. All right, so we'll fix that later. Now, we want to know what the change in kinetic energy of this object is if an impulse I acts on it. So let's just remember, kinetic energy, whenever there's momentum or impulse mentioned, is p squared over 2m. So we know that impulse is the change in momentum. And so we're going to go from an initial momentum of 0 to a final momentum, pf, which I'll just call p. And we know that the impulse is equal to I, so we know that the impulse equals this momentum, or the number is. So that means the kinetic energy is going to be I squared over 2m, and that's how I'm getting choice A. So those are all the questions in this little mini packet. I have plenty more energy questions and work questions for you to do if you want some more practice, but I wanted to kind of give you some solutions so that you had a guide as to how to do these problems and study.